Hello, my name is Hakim Jemaa, a PhD student from KAUST, and let me present to you my thesis, Bridging the Complexity Gap in Terahertz-Band Transceiver Design. The future of communication is not simply building faster internet. The next leap in technology is a world that actually perceives its surroundings. As we can see here, in the near future, we'll be reaching a reality where devices won't just share data. They will sense, image, and map their environments simultaneously. How do we achieve this? By unlocking the terahertz band. Terahertz waves offer more than just a promise to achieve 1 terabit per second data rates. Because of the ultra-wide bandwidth and small wavelengths, they allow us to merge communication, high-precision localization, and even material sensing into a single wireless signal. The scale of these applications are breathtaking, ranging from guiding autonomous vehicle networks and drone fleets all the way down to nanosensors transmitting real-time diagnosis. With great promises comes great challenges. This is what we call the baseband complexity gap, where we have thousands of bits per clock to process, ultra-high correlation, energy and latency constraints. To respond to this, 4 pillars in our work. First, an accurate representation of the terahertz channel. Secondly, promoting low complexity and parallelizable data detection. Thirdly, efficient channel code with the use of short codes and low complex soft information. And finally, a performance analysis to quantify the gaps and guide future designs. You can't build a realistic transceiver without first mapping its chaotic environment. Now, the terahertz waves significantly differ. They suffer from the severe frequency selectivity, the misalignment, the beam split. In order to model this complex reality, we developed TeraMIMO, a 3-dimensional end-to-end channel simulator. By meticulously modeling these physical impairments, we accurately say that it is the terahertz channel that should drive our design choices, not the other way around. Next comes detection, what the receiver does to recover the transmitted signals. Since we are dealing with high correlation and high dimensionality, brute force or linear approaches don't scale anymore. We need something in between. This is why we advocate for subspace detection. By using a special decomposition on the multiple input, multiple output channel, we can transform the detection problem into an independent layer search. Each layer runs a small search, and we run these searches in parallel across the different layers. On top of that, our proposed detector orders these layers strategically before detection and performs a selection of which layer to be transformed and how, balancing performance and complexity. So we move from a traditional MIMO detector to a parallelizable and efficient subspace detector. Since we are in wideband, we can transmit over multiple frequencies. One idea here is, what if we do not repeat computations across all subcarriers? What if we compute certain operations once and reuse them for others? Our proposed reuse strategy groups nearby subcarriers according to specific criteria and reuse the heavy operations that are computed within each block only once. On top of that, by mapping space, time, and frequency resources effectively from the source, parallelism isn't just inside the detector, it propagates through the baseband chain into decoding. In terms of results, we reach up to 25% less complexity in wideband detection, in addition to a full parallelizable chain, and up to 5 decibel in performance gain compared to regular subspace detection while using 50% less operation. Efficiency, parallelizability, and low complexity are the key to future reliable communications. Thank you.